to YouTube. So I started recording a little bit early. You don't have to pay attention if you don't want to, because I'm just working on setting up LogicSim to go back to where we left off from the previous lab, so I can finish it today so that you guys can see the finished product. Alright, so now I have to go find my OBS screen, which is here. There we go. Alright, so you should be able to see my OBS screen at this point. Oh, okay. Alright, I'm back. And let me reshare that screen. OBS is right here. There we go. Alright. Alright, so what you're seeing, what you're looking at is the module that talks about binary addition. And this is LogicSim. You know, I've been working on this for a little bit. So I'm just recreating where we left off from the previous lab. So this time I can finish it just like what you had to do on last Thursday. So I'm just putting the gates in, just need one more exclusive OR, do the same thing. And you're correct, I did not save my file either. So I just kind of quickly recreated everything, which is not too bad. There we go. And the Discord side has started already, you know, in the voice channel. So let me add myself to a voice channel first. There we go. So I am now on the voice channel on Discord, as well as on Google Meet has me muted. So now I'm good on both sides. We should be good now. Yes, we are good. We are doing Google Meet because the class size is exceeding 50 people, and as a result, you know, we have to keep using it until. I mean, I hope we will never get to that point, you know, where the class size is less than or equal to 50 people, because we are starting with 70 people. So I really don't want to have 20 people to drop the class. Alright, so I think both sides are going now, and so is the YouTube live stream. Alright, so looking at the time, we got 5 more minutes, and I think we can get back to the point where we left off from last time. Okay. Alright, so we just need X to go here, and go here, and then Y. Oops. We need Y to go to the all of the other pins, the output, the input ports. So one over here, one over here, and one over here. So the output of this is going to be G, the output of this is going to be P, and then the output of this is going to be Q. And now we slap the K1, K2, K3 circuits into this main thing. So we got K1, K2, and K3 here. And now the hookup is really easy because they're all just going to be this is what we call a multi-dropped type of topology or connection topology, where you have one single net or single conductor that is going to the equivalent port of all of the components. So we hook up all the G's, and then we hook up K0 all the way from here. There we go. So I'm a little bit slower than some of you because I'm older than most of you. And then two is I'm using a touch point on my IBM keyboard or Lenovo keyboard. So a touch point is really a wonderful thing because you don't need a mouse. Because I'm lazy. Because I'm lazy, I'm not using the tunnels. Alright, so this is Q, which is not useful at this point. And then what we need to do is to look at the output. So let me just first create the two output pins. One is the sum, which is a 3-bit wide output pin. And then the other one is K3, which is a single bit output pin. So here's K3. So K3 is the easy one. Yeah, those things are still a thing on some of the Lenovo laptop computers. I think it's only on their ThinkPad line of laptop computers. If you get an IdeaPad, it doesn't come with that anymore. So only on ThinkPads. So Nathan is correct. It is exclusively on ThinkPads. Most people don't like to use them anyway. I really like my the touch points because my finger doesn't have to leave the keyboard at all, so they can stay at the home position at all times. Oh, I'm glad to know that. It's harder and harder to find keyboards with that built in. So even though I'm using an external keyboard, I'm using one that has that. All right. So apparently people are still trying to join the Google Meet from outside of the Los Rios network, and that's why I need to go let people in. All right. So here's the most tricky part, which I'm not going to do until the whole class is here. So we'll wait a little bit until the whole class is here. Well, or at least until 5:30. Um, hmm. Okay, so 2 questions you answer. Um, all right, so Nicholas has already answered the question of the uh, nimbles. I don't call them nimbles. It's called a touch point. And then the other question is, can we let everybody in? And I don't really want to let everybody in because right now it's restricted to Los Rios people. So can we get a Google Meet bomber? Yeah, but if I leave it like wide open, then we can have even more, Google Meet bombers. So that's kind of why I'm not switching that default. Yeah, there is an official name. I think the official name is a touch point. Let me look it up. So if I go to settings, go to mouse and touchpad. Okay, there we go. So the official name is a track point. So I stand corrected. It is not called a touch point. It is called a track point. They're fun to use. I used to play video games with it too. You can kind of imagine that can be a little bit interesting to kind of play video games with a track point like that. Alright, here comes another one. Alright, so let me take a look at the time. Oh, okay, so it's time to get started. Perfect timing. So it is 5:30, and I'm gonna get started here. So I'm just recreating the circuit to the point of, the starting point of where you guys start on last Thursday. So I'm getting to the point where it is really kind of important is how do we compute the sum now that we have K1, K2, and K3, and they're pretty easy to hook up on one side, which is the input. All the P's coming from the multi-bit OR gate. All the G's are coming from the multi-bit AND gate, and K0 is just K0. Okay, so there's nothing too difficult about this portion. Okay, this portion of the circuit is actually pretty simple once we know, what is the AND gate, OR gate, and the exclusive OR gate is doing. Now, the other side is, we want to compute the sum bit. Now, this is the important part, okay? Because I got some questions about this the other day. Is how do we figure this out? Okay, I'm not really sure how people think. Okay, but I can tell you how I think. Okay, so I look at the sum bit and go like, what is the equation that is specific, that applies to the sum bits, right? So if you read up the notes, you will find that, oh, this is the single digit result of adding 2 digits. Okay, that's just that's regardless of whether it's binary or base 10. So R of something. Okay, but this is a circuit. We want to use a logic gate to get the job done. So now we have to say, so instead of having x plus y and then the whole thing mod the base itself, which is not a Boolean function, now we need to find out, okay, how is the Boolean function done? And then in my notes, there is a place that says specifically that in base 2 or in binary, the R function can be done using exclusive OR. But because we don't use exclusive OR as a logical operation in C and C++, let's do this using, a whole much longer expression using just AND, OR, and NOT. So there's a little paragraph that talks about that. That is kind of what I need you guys to do, is to read the notes, but not just to glance through the notes, but really to make the connections. And that's partially what the lab is for, is to help kind of make all the connections, because now that you have to do it, you kind of have to think back and ask yourself, where is it defined? Can I negate any one of the input instead of putting separate NOT gates? Yes. So input ports can be negated. So the individual input ports of a gate can be negated. So if you click on one, you can see I can negate the top or the bottom or both. So yes, you can do it that way. In other words, if you want to turn this into a subtractor, it's super duper easy, because you just have to go to these two and negate the port that connects to X, and then it immediately becomes a subtractor. It is that interesting. So anyway, so getting back to how to compute the sum, well, at least in this circuit, it is the sum. If I had a subtractor, it would have been the difference. So anyway, so once we looked it up, we found that it is a exclusive OR that we need. So we already got an exclusive OR gate of the right shape and the right number of input pins. So we just want to make a duplicate of this, okay, and just kind of slap it here. And the output of this becomes the sum. Cool. Now the question is, what do we hook up to the input of the exclusive OR? So one input is Q, and this is Q here already. So that one is pretty easy to figure out. We just have to wire this all the way to here. Then we are done with that one. The next one is go like, okay, so from the equations, we know it is the exclusive OR between the Q bits and the K bits. And we got the K's in loose pieces, right? We got K1, K2, K3, and then K0 here. Most people, at least initially, would use K1, K2, K3, put it into a merger, and make the merged end of the splitter or the merger connect to this particular input port and call it a day. Okay, and that would not be correct. So let me just do this, because I want to show you guys, what it looks like. So we'll make the phasing. Okay, wrong thing. I have to select the thing that I want to flip first. Okay, there we go. So we'll flip the direction like that. I mean, there are different ways to flip it. This is just one way to do it. And we know the merged end would go to the exclusive OR gate, so that's pretty easy. And then some people, okay, decided to do it this way because I suppose it is the intuitive thing to do, because these are the things that they are not connected yet, and there are 3 split end to connect to. But this would be the wrong answer, right? And for people who asked about this, okay, who asked, does my circuit look right? I would reply with a question. Okay, the question that I ask is, how is S0 computed? So if you think about the least significant bit of the sum, it is the exclusive OR between bit 0 following this wire of the output of this exclusive OR, which is cube 0. So cube 0 is fine. But if you follow the other port, it would be K1. I mean, you're not going to exclusive OR K1 and Q0 to compute S0. You have to exclusive OR with K0. Okay, Q0 exclusive OR K0 would be S0. So that is why this way of wiring up is incorrect. So now let me undo that. Okay, so the bit 0 has to come from K0. So we can always just kind of get it from here. This is gonna look ugly somewhere. Okay, but that's fine. Looking ugly is not a big problem. And then K1 goes to bit 1, like that. And then K2 goes to bit 2 of the splitter. That would be correct. Alright. I think Jonathan means that the ordering, well, if the ordering is K1, K2, and K0, going in this direction, that would also be wrong. So I think there was one person who got the ordering wrong. In other words, that person did connect K0, K1, and K2 to the split end of the merger, but the ordering was incorrect. So that would also still be wrong. Oh, okay. All right. No, this is the answer. Okay. All right. So how do we test this, right? Since we kind of have talked about base conversion, you can test this actually, right? I mean, you already know, how binary addition works. So all you have to do is to give it some numbers. Now I know, there are, let's see, there are 7 bits as input, so there are 128 test cases. Technically speaking, there are 128 test cases. So it may not be feasible to do everything by hand, but you can at least test a few, right? So you can have 1, 1, which is representing 3, plus the 1, and then the output is 1, 0, 0, which is 4. That's good, right? You can have one more. Okay, so we have a 7 as x. 7 plus 1 is 8. But 8 cannot be represented only using 3 bits. So we have K3, which is outside of the sum, being turned on as a 1, whereas the 3 bits are zeros. So basically the answer is a 0, but we have a carry that is representing a value of 8. That would be correct. Okay, so there are several ways to test this circuit, just by poking these bits and making sure that whatever the answer is what you're looking for, or what it is supposed to be. So that's kind of the answer to the previous lab. Are there any questions about this lab? All right, I'm not seeing any questions. So if we don't have any questions about this part, we're gonna move on and talk about signed number representation. So let me go back to Canvas, and I will point out which module we are on, which really should not be a big surprise, because all I do is to move, just in a single direction. So we were done with binary subtraction last Thursday, and now we are going to signed value representation. So this is the module that we are going to be talking about today. And let me use the full screen. There we go. And with this one, it is rendered last year. So if you right click on the formula, it's not going to show you the tech result, which is fine. I mean, there's nothing too tricky about this one. Okay. All right. So assuming that you guys have at least read the module, may not be understanding everything, all the way down to the equations and the expressions. This is about how do we represent negative values using just bits. Okay, so when you can only have zeros and ones because transistors are either a particular wire on a circuit board or inside the processor either has a low voltage which is representing a zero or high voltage which is representing a one. So how do you represent something that is negative? Some people would say, well, can't we just use one bit for the sign and then use the rest of the bits for the absolute value? So this way we can just say one part will say how far, and then the other side, the extra bit is going to say in which direction. That's one way to do it, but it's not a very friendly way of doing it. Okay, because it's not friendly in the sense that if you want to add numbers that are signed, where you can have positive and negative values, you kind of need to do a whole bunch of modifications to the circuit in order to make that work. Okay, so there's an easier way to do it, easier in the sense of logic gates, but less intuitive in the sense of what is that. Okay, so we'll go ahead and talk about this. Okay, and with a tablet, it is actually going to be easier to talk about this because I can actually show you graphically, how to visualize, how values are represented using a fixed number of bits. So let me turn on my tablet first. There we go. And I'm going to fit the screen. So I have changed the approach, so that this way it is. I just have to manually move it around, to make it visible and then invisible. There we go. Okay, the bottom is still like that. Okay, and I know my video is overlapping a little bit, but the actual screen area is smaller than that, so it really should not be an issue. There we go. All right. So I'm pretty sure all of you are familiar with the concept of a number line, right? Okay, so let's go for a number line first. In fact, we'll go for a natural number line. Oh, it's not showing. All right. And I think the second time I start this, it will work reliably. I still haven't diagnosed what the issue is yet, but that's a personal project for another day. There we go. And then move it.
What part of the addition module was the sum in?
I'm not quite getting the entire voice. Can you repeat the question?
What in module 023 or 83, the addition one, where was S sub 0 described or defined?
Aha. Okay, so let's go back there first, and we'll find it. Okay. So some of this stuff, can be a little bit hard to find. Not because I intentionally write it, as a uh, to be difficult, but sometimes the topics are just kind of linked in a way that's not easy to find. All right, so what we want to do is to start from the bottom and then work ourselves back up. All right. So how does the computer do this? Using transistors. Basically, it's converting from arithmetic versions of C and R to the ones that only make use of Boolean operators. So that one, R is here. Okay, so the part that talks about R is right here, and it does mention that we use exclusive OR to implement the R function. But this one does not specifically say, hey, the sum bit is going to be related this way. So if you go up a little bit, there's a discussion of the sum bit, S bracket something. So right here it talks about the sum bit. So S1 is the R of Q1, K1. And this is the general version of it, which is Si is the R of Qi, Ki. So there are two steps to the whole process. One part talks about SI is the R function applied to QIKI, and then the other part, which is down here, talks about how R can be implemented using exclusive OR.
Gotcha.
Yep. So it's how we make that mental connection. That's going to be the important part. And it's not really only for this class, and it's not only for when you take classes at a university or a college. It is also important when you um, learn how to do programming. On the job. Because a lot of times the manual is not even written by a person anymore. They just extract the comment, from functions, using an automated tool, and a lot of times, we have to kind of put all the pieces together in our head, which means when we are reading, it's kind of important to track what we have read before and then mentally make the connections between the pieces. And this is also why, it might be helpful to write notes for this class. So when you encounter a definition, you just kind of write it down on a separate piece of paper or a separate document. So this way, at the end of the class, you can basically filter out all the fluff, okay, in my module, but then you can focus on all the important equations and formulae. So now it is easier to make that mental connection between the major pieces. So that's one way that I can recommend people to do. Not sure how much it's gonna help, but that's one way to kind of help in the process. So getting back to signed value representation, and now we are looking at a number line. So for all of our discussion, let's just say that we are using 3 bits. Okay. In other words, the number of digits is going to be finite. We basically have to say, okay, we are representing all the values only using X number of bits, okay, because that's how your processor works. So with 3 bits, we can enumerate all of the ways of combining the zeros and ones. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and then we have 1, 1, 0, and then 1, 1, 1. So those are the 8 ways to combine zeros and ones in a 3-bit organization where ordering is important. Okay, where a 0 or 1 is significant. So now we look at this. Now each one, okay, if you look at the bit patterns, each one really does not have an inherent meaning to it. So when you read this, you can say, oh, we know base conversion. I know 0, 1, 1, is base 2's way of representing the quantity of 3. That would be one way to interpret 0, 1, 1, because 0, 1, 1 can be just 3 pixels on the screen using a monochrome monitor, where you have a dark pixel, a white pixel, and then a white pixel. That's it, right? Which is not a number. So you kind of have to remember, a certain bit pattern may not be representing an integer value. It may not be representing a value that, in the sense of a number. It can be representing pixels on the screen. It can be representing, where to put a dot, on a printer, and so on and so forth. Okay, so there's no inherent meaning to bit patterns. Okay, they are really just a bunch of zeros organized in a certain way. All right. But since the discussion we want to do here is to say, but how do we associate values with the bit patterns? So with 3 bits as a natural number, okay, it kind of makes sense that we start with 0, 0 here, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then finally we have 1, 1, 1. So in this sense, if we write the base 10 representation of these values, then we have 0, 1, 2, 3, 4, 5, 6, 7. No surprises, right? That's pretty straightforward. But then the problem is What if I just add 1 to 111, which is representing 7? Then you guys would go like, then we get 1, 0, 0, 0. And I'd say like, nope, we cannot do that because we are only using 3 bits. So that means, whatever the result of 111 plus 1 is, can only be 3 bits. Oh, tech. I just remembered, in when you were testing the circuit that we were, talking about earlier, you just did that, okay? 111 plus 1 is 0, 0, 0. So that means the next item here is going to be 0, 0, 0. And you cannot call that 8, right? Because, it has the same representation of 0. So, it seems like we are running out of values, okay? This cannot be a number line anymore. So that's why in this class I introduced the concept of a number circle. So now, instead of drawing a line, we draw a circle. So with a circle, we still need the 8 slots, okay, the 8 points. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. So we now have 0, 1, 2, 3, 4, 5, 6, 7. Okay? And now it is a circle, which means if you add 1 to 7, we go back to 0. Perfect. So some of you may be thinking, is that real? I mean, Tech, it doesn't seem to make sense that when you add 1 to the largest value that a bit pattern can represent, we just get back to 0. That doesn't seem to make sense. It actually makes perfect sense. You can actually test this using a C program. Okay, I'll go ahead and write a very simple C program so you can see that. Okay. I mean, do you guys want to do that, or do you think you got the idea already and we don't need to spend the time to do it?
I'll maybe see a quick example.
Okay. Okay. So more people want to see it, then I don't see any objection, not even through the direct messages, which is okay, fine. Online GDB. This is now my favorite C programming tool just because it's web-based and it's easy, right? Alright, so what we'll do is we take out print hello world. I don't really have to do that, but it doesn't need to be here. Okay. Even hello world? I'm just joking. Alright, so let's go ahead and get started here. I'm going to start with unsigned. Okay, so this is also a good place to start to introduce the concept of stdint.h, standard integer.h. So I'm pretty sure most of you do not have exposure to this particular header file. You can look it up, okay? Just look up, in Google, okay? You'll see, and then stdint.h. Just don't look up stdint.h by itself because otherwise it would interpret it as a domain name, which wouldn't work. So the idea is, with this header file, we can now start to use types like this: uint underscore t x. So this means x is an 8-bit unsigned integer. And then we can have a bigger one, okay, uint16 underscore t, and we'll call this y. And then what we'll do is we're going to write a loop here. Okay, so they are both going to start with 0, x equals 0, y equals 0. Y being the wider integer can go beyond 255. So I'll make y stop at 1000. Okay, and then the post operation is incrementing both x and y. So both x and y are going to be incremented here. And then in the loop body, all I'm going to do is to do a printf, and we'll print. Oh, I have to remember how to specify the width of an integer when I'm printing. That, or I can just cast it to a regular unsigned. Yeah, I think I can do that. We'll just cast it. So we'll do a %u, which is an unsigned number. We'll say x equals to %u, y equals to %u, \n for the line feed. and then we have unsigned x, and then unsigned y. So I'm doing the casting without using specifying the width, because that is what printf is expecting when it is using %u to specify an unsigned base 10 representation. So now we put a semicolon here, and I think this is it. We'll go ahead and run the program without using the debugger. There's no need. Yes, I do have to specify this is a C program. Alright, so it has just printed a whole bunch of stuff here. And if I scroll, well, I'm not even sure whether we can scroll all the way back, but we can see the transition point right here. So you can see how when y is 767, x is 255. I mean, that part should be suspicious already, right? Because, how come they're not the same? But the next line is even more suspicious, because x went all the way to 0, and then y just went forward to the next available value. Okay, so if I think it might have kept the entire buffer, so we can see all the transitions here. So right here we can see x equals to 255, y equals to 511, which is also suspicious because, how come they're not the same? But the next line illustrates what I wanted to say, because when you add 1 to x, it became 0. But when you added 1 to y, it became 512. So now we go back to the first point when this happened, which is right here. Okay, so up to this point, x and y had exactly the same value, 255. But when we added 1 to x, it went all the way back to 0. But we added 1 to y, it went to 256. So that is the whole idea of what this is trying to illustrate. Except I'm not using 8 bits, because it would take me a much longer it would take me much longer to write the circle when we have 8-bit numbers. 3 bits is big enough that we can actually see some values and do some operations, and yet it is easy for me to kind of hand draw the entire thing. So are we good so far? Yeah, go ahead.
I don't know if I'm completely off the mark here, but is this kind of like a clock? Like, it keeps 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I mean,
it is not a clock in the sense that there's no hour hand, there's no minute hand, there's just one hand. Okay, we can only represent values from 0 to 7. There's no way to represent 8. Is that okay? If you add 1 to 7, you get 0, not 8. It's not exactly an underflow. It is it is not overflow. We don't call it overflow, but you are basically going back to the smallest value. In some sense, it is like a wall clock, but the wall clock has a hour hand, so it can represent more values than just the numbers or the values on the clock face. Okay, so but there's a way to fix this. Okay, so basically, when we perform operations using this type of representation, what we are really doing is, when we say x plus y, we are implicitly doing a mod 8 in this case. So every time we add, every time we subtract, there's always a mod 8 in it. Is that okay? In other words, we're using modulo 8 arithmetic in this case. Everything is always, all the operators in arithmetic, they're always, when you're done with the operator, they're always modded with 8. It is well, I mean, it's finite. The domain is finite. Okay? So are we good so far in terms of, when you have 3 bits and you want to represent non-negative integers, you can only go from 0 to 7.
Only question I got is how do you know when it's either 0 or 8 if they're the same thing, if they're both 0, 0, 0?
The answer is easy. There's no 8. There's
no 8.
only 0.
Okay.
Yep. We cannot represent 8 using 3 bits, period. Is that okay?
Yeah, it makes sense.
Okay. All right, so now the question is, how do we represent negative values, right? So if you think about this, okay, I'm just going to use the cursor on the tablet to do this. When we are rotating in the clockwise direction, we're incrementing. When we are rotating in a counterclockwise, fashion, we are decrementing, right? I mean, that seems kind of obvious, okay? So now the question is, where if I had to find a place to put a -1, where would be a kind of logical way to put it, right? Which side of which number does it belong? This is not base 7. Base 7 means we can represent 0 to 7, 0 to 6 with each digit. This is base 2, but using 3 bits. It's a 3-digit binary number. On the far left, okay, but it's a circle. You cannot say left or right in a circle. So to whose left? Okay, we know it's to the left of something. To the left of 0. Yes, 1, 1, 1. Okay. So what I will try to do now is to use a medium thickness line and gray to represent the negative values. Okay. So now we say, hey, 1, 1, 1, I want you to also represent -1. And I'll put these in circles too, in parentheses, so it's kind of clear that, we are differentiating where the negative values are going to go. Left of 0, yes. And then where are we going to put -2? Well, kind of makes sense to put it here. -3 goes here, and then -4 goes here. And then somebody's going to say, oh, I know, the next one is going to be -5, and it's going to be 0, 1, 1. Actually, that is not the case. Okay, so we are not going to represent -5. And now the question is, but why not? Well, because we want things to be balanced. Okay, we want half of the circle to be representing negative values, and then the other half of the circle to be representing non-negative values. Not positive, because 0 is neither, so we want half of it to be negative, and then the other half to be non-negative. So if we do a split like this, we can see 1/2 is representing negative values, and then the other half is representing non-negative values. And that is how we partition the circle in terms of assigning values to the bit patterns. Alright, so we got a few people typing. I'm going to take a pause here, and then we'll ask. Oh, that's a very good question, Victor. I will answer that question with a very, some people would say, pointed question, but I will say I will argue otherwise. But we'll go ahead and wait until the rest of the class start to finish their typing, and then we'll go in and answer these questions. I like it when people ask questions because it means they're paying attention, they're thinking, and they're finding something is like, hey, this doesn't seem to make sense. That's good. All right, and then the next question is, so Nor took the thunder out of my out of my answer because he is absolutely correct. I'm assuming Noor is a he. And then Jonathan said, is the negative side always go 1 more than the positive side? Yes, because the non-negative side has 0 in it. And 0 counts as a non-negative value for the purpose of the circle. Yes. So Andrew, that is correct. If you want to use modulo math, so that is correct, because that's basically the integer set with mod 8. All right. Why are we having it? Because we want 1/2 to be negative values and the other half to be non-negative values. And then Caleb said the range of an unsigned base 2 is, yep, that is correct. I'll get to that part too. I'll get to that part. So right now the focus is what Victor asked. If it wasn't halved, what would occur? It would basically throw a wrench into the adder and the subtractor mechanism that we have already derived. And then Jonathan said, so 3-bit can only represent -4 to 3 if we choose to look at it as signed representation. Yes. And Victor is also correct that with 3 bits we can only have 4 negative numbers. That is correct. Okay. All right. So there are a few questions. So we'll go back and start with Victor's original question, which is, so how do we know? Okay, let me just kind of use my pen here, and we'll go back to a thin and dark line. So the question is, if we just kind of take a look at this portion here, the question is, when we look at the bit pattern 111, okay, you apply the tiny little voltmeter, to the output of transistors inside the processor, and you see 1, 1, and 1, okay? So now the question is, what is it representing? Is it a 7 or is it -1? And then my answer is, why do you care? Why do you care whether 111 is representing a 7 or a -1? You don't need to know if you are adding. You don't need to know when you're subtracting using the adder and the subtractor that we have talked about. It works out in both cases. That is the beauty of using assigning negative values in this particular fashion, is as long as we are not out of range. Okay, the adder that we have talked about, the binary adder, the carry look ahead adder that we have talked about, and then also the carry look ahead binary subtractor, it will work regardless of whether we are representing signed versus unsigned values. That is the beauty of this type of representation. And as a result, if you're just adding or subtracting, we don't need to know whether the bit pattern is representing a signed versus an unsigned value. Not at all. Okay? So now we will go ahead and, I will give you guys a few equations. Okay? So the largest, so you might want to write this down, or at least write down the time mark so you can get back to this point. So given n bits, okay, so n is typically 16. It starts with 8, and then we went to 16, and then 32, and then 64. So you can kind of imagine the next one up is going to be 128. This is basically referring to the natural width of the ALU, the arithmetic and logic unit inside the processor. How wide is that mechanism? Okay, in other words, using a single clock, okay, what is the width of the bit pattern that it can handle just by using one single clock. So now, given n bits, okay, using the unsigned representation, the values we can represent, the lowest one is always 0. The highest one is not really surprising. It is 2 to the power of n minus 1. So if you look at the circle, it kind of makes sense, right? We start with 0, and then we have 1, 2, 3, 4, 5, 6, 7. And 7 is indeed 2 to the power of 3 minus 1. That minus 1 has to do with 0 is taking one spot already. So that's why we need to do a subtraction of 1, because we cannot have 8. So do we have any questions about the about this equation over here? Let me move the mouse pointer out of the way. Alright, so we got a question. This is why there's a limit of integer numbers representation within programs. Yes. And why it rolls all the way back to 0 if you get to 2 billion or something like that. It's actually 4 billion. 2 billion is for signed representation, and then it wraps around to -2 billion something. Which is even worse, right? So, but that's a good lead in to the next discussion, which is in signed representation. What would be the range of values? So it goes from -2 to the power of n minus 1 all the way to 2 to the power of n minus 1, the entire thing minus 1. Is that okay? So Caleb is correct. If you use only 32 bits, in terms of the largest unsigned value, it is 2 to the power of 32 minus 1, which is 4 billion something. I cannot remember the rest of the digits, but it's 4 billion something in base 10. Alright, so do we have any questions? Do we have any questions about this part? No questions. Alright. So if there are no questions, then the next question I have is, if I give you a negative value, how do you find out its binary representation given a certain number of bits? That's the question. I'll give you a particular example. Okay, so I'll say given 3 bits, how do we represent, say, -2? Okay, you guys will go like, oh, that's easy. We just look up that number wheel and it is 110 in the wheel. Sort of. Okay, but what if I'm asking you, given 64 bits? Okay, how do we represent -183? I would like to see someone to draw that circle out, right? So Nicholas is correct. Nicholas is saying, invert the bit, then add 1. But the question I have is, why does it work? Okay, just because it works is usually not good enough for me. I want to know why it works. Okay, and some of you can disagree with my way of looking at things and go like, all we need is to know how it works. We don't need to know why it works. Okay, that's okay. I'm not going to engage in philosophical discussions because maybe you're right. Okay, maybe we don't need to know why. But I personally need to know why when I encounter something like this. Alright, so what I'll do is I'm gonna how should I put it? We'll do some observations. How about this? We'll do some observations first. So the observation is, if you subtract the negative value represented by a bit pattern from the positive, the unsigned representation, you get 8 in here. 6 minus -2 is also 8. 5 minus -3 is also 8. 4 minus -4 is also 8. So there's a pattern to it. Okay, and that pattern really has to do with how far is the negative value from 0. Okay, and how we assign the unsigned value in a positive way. Okay, so there's a certain pattern to it. So given that particular pattern, okay, so getting back to what we're trying to do, we now say 0 minus 2 is really the same thing as using only 3 bits. It really is the same thing as 8 minus 2. Why? Because 0 and 8 are really the same thing. But then somebody's going to say, but Tech, this is totally wrong, because as you said earlier in class, looking at a circle, there's no way to represent 8 using only 3 bits. Then I'll say, you're right. Thank you for your correction. Okay, so how are we going to do this? Well, we can say this is 1 plus 7 minus 2, can't we? I mean, after all, 8 is really just 1 plus 7, right? I mean, I don't think anyone's going to argue and say, no, Tech, 8 is not 1 plus 7. Alright, so now we say, let's regroup things a little bit. We put parentheses around 7 minus 2. Okay, we can do this. Okay, this is algebra, right? I mean, this is called the associative law, where you can instead of putting parentheses around 1 plus 7, we can move the parentheses to 7 minus 2 in this case. Okay, big deal. what is the big deal here? Well, the big deal is 7 minus 2 is also 2's negation. Hold on a second here. What do you mean by that? So in 3 bits, okay, 7 minus 2 is the same as tilde 2. Now, if you have never learned the tilde operator in C and C++, it is called the bitwise not operator. Okay, we are basically negating each individual bit within a bit pattern. So, for those of you who think, I don't think so, well, let's work this out. Okay, we'll work this out and see whether that actually works or not. 7 is represented by 1, 1, 1. 2 is represented by 0, 1, 0. And we can look that up from the number wheel itself. So now we do a subtraction. There's no borrow, right? Because there's no 0 minus 1 whatsoever between the x and the y. So we don't really need to handle the borrow in this case. So we just do the subtraction. 1 minus 0 is 1. 1 minus 1 is a 0. 1 minus 0 is a 1. Right? I mean, in base 2, that's how things work out. Okay, let me just emphasize that these are all in base 2. Okay, so what? Well, now we do the bitwise not. So when we perform bitwise not of 2, then we are looking at 0, 1, 0, and we basically just do a negation operation so that the 0 becomes a 1, the 1 becomes a 0, and then the 0 becomes a 1. Ooh, wait. We get the same result here. How does it happen? Well, it happens because when you have a 1 minus something, and as in a arithmetic operation, it is the same thing as a negation. There are several ways to look at this. Okay, there are really several ways to look at this. You can look at this from the perspective of a truth table. Okay, and you basically say, okay, here's an independent variable x. X can be a 0 or 1. Now we look at 1 minus x as in an arithmetic operation. And now we look at the negation of x as in a Boolean operation. Okay, so you say 1 minus 0 is a 1. The negation of 0 is a 1. 1 minus 1 is a 0. The negation of 1 is also a 0. So in the truth table, we can see that the two columns representing the two expressions that we want to check, they indeed have the same value for each row. So that means they are equivalent. So this is one way to think about it. Okay, but this is only looking at it from a 1-bit position, which is fine because this 1 here is not a variable, because when we use this 7 here, it is a power of 2 minus 1. And that's why it always works. So now, when we look at the concrete example, now we say, what about, we have n bits, okay? In other words, the width of the binary bit patterns is n, and the value, to negate, to arithmetic negate is x, okay? So we are generalizing. So now we still have 0 minus x is 2 to the power of n minus x, because everything is modulo 2 to the power of n. So that's why 0 and 2 to the power of n are considered really the same thing, okay, when you perform operations like this. So now we can say, okay, so now we have 1 plus 2 to the power of n minus 1, the whole thing minus x. Okay, and this one is really just to avoid that we have to explicitly represent 2 to the power of n. So when you look at this expression, 1 can be represented using n bits. 2 to the power of n minus 1 can be represented using n bits, and x obviously has to be an n-bit number itself. So now we look at this and then we rearrange things a little bit. It becomes 1 plus 2 to the power of n minus 1 minus x. And I'll put extra parentheses around this, okay? That's really just by regrouping the parentheses, because because of how algebra works out, right? And now we say, oh, but 2 to the power of n, the whole thing minus x, is really just the bitwise knot of x. So now we have 1 plus the bitwise negation of x. That is why it works. This is why. This is what we call 2's complement. 2's complement comes from the term of it is 1 plus 1's complement. This part here, okay, I run out of space on my virtual paper. This is called 1's complement. Okay, negation. Bitwise knot is 1's complement. When you add 1 to 1's complement, that is called 2's complement. Alright. Alright, so I'm gonna pause a little bit here, and I'll finish up 2's complement first. So the 2's complement of x is really just 1 plus the bitwise knot of x. The tilde symbol represents bitwise knot in C. So I'm going to pause. I will let you guys ask questions just to make sure that we get all of these points. Yes, so what Andrew is saying is, we do not want to use 1's complement as a way to represent negative values, because it will need extra circuits to perform addition and subtraction. So it's not like it cannot work, it's just that it is not very efficient. And we basically cannot reuse the adder and the subtractor that we already have, which is kind of a pain. All right. So it would appear that we don't have a lot of questions. I'm just looking at the text channel. And I'm drinking my coffee so I can teach even faster after this.
I just needed some quick clarification. I think you already said it, but you said 0 is equal to 2 to the nth power minus 1?
Nope. I said 0 is the same as 2 to the power of n.
To the power of n. Okay,
Yeah.
gotcha.
So basically, it is saying, 0 and I times 2 to the power of n, they're all the same. I is an I being
Right.
an integer.
Okay.
Because everything is mod 2 to the power of n.
Okay, thank you.
Mm-hmm. This is a C, and that's a 2, so it's C2 of x. It's in the notes too. The module that I typed, that I asked people to read before class. All right. So let's check this out, okay? We'll work out a few examples, just to see whether it works or not, okay? So we'll first apply it to, I don't know, let's fix the number of bits first, okay? So n, which is the number of bits, let's make it 4, okay? Because 3 is already done and people can just easily look up the number wheel that we have already. Let's not do that, okay? Let's do n equals to 4, and we want to find out what is 2's complement of 5, which is supposed to be representing the value of -5, okay? Because 2's complement is really the same thing as arithmetic negation. So we'll work this out. So 2's complement of 5 is 2's complement of the binary representation of 5, which is 0, 1, 0, 1 in base 2, because we have to use the right width, okay? If we say n equals to 4, we have to use exactly 4 bits to represent the value, which then becomes 1 plus the bitwise knot of 0, 1, 0, 1 in base 2, which is then, which is then 1 plus 1010 in base 2, which is then 1011 in base 2. And people look at this and go like, well, Tech, you can say whatever, because you are the one who said that this will work out. We have no idea whether -5 really is represented as 1011 in base 2, signed, using the signed representation. So let's do something with it, okay? There are two things that we can do with this that can potentially be interesting. So what we'll do next is to use 2's complement, but this time we apply it to -5. In other words, this is the computer's way of finding out what is the arithmetic negation of -5. Well, what is the arithmetic negation of -5? We should get 5 back, right? So this is a kind of cool way to check at least whether it is self-consistent or not. Okay, so we'll work out the math here. Okay, I'm messing up somewhere. Oh, 1011. So I copied the values wrong. No wonder it's like, why? How is it off? There we go. Oops. There we go. Wow, isn't that magical? It does seem like, the 2's complement is doing the same thing as arithmetic negation. Okay, so if this is really the case, if -5 is being represented by the bit pattern of 1011 in base 2, and Tech said, this means, we can reuse the circuits that we have talked about in terms of addition, subtraction, and stuff like that, right? Let's see how it works, okay? So we want to say, give me 3 minus 5, okay? I want to subtract 5 from 3. Now, without using anything that we learned in this class, just using algebra, we can now rewrite this as 3 plus the negation of 5, which basically means this should equal to 3 plus the 2's complement of 5, because 2's complement is the same thing as arithmetic negation, okay? So now we are saying this should equal to 0011, which is how we represent 3 using 4 bits, plus the 2's complement of 5, which we already know is 1011 in base 2. Alright, so now, you guys would go like, how do we know this is true, right? So let's go ahead and practice, how we do binary addition in this case. So we have 0011 plus 1011 in base 2. This is x, this is y, this is q, this is k, and then we have s over here. Yes, we just talked about these things at the beginning part of today's lecture, and trust me, that was not planned. It was not planned that we would talk about that, and then we actually get to this point where we'll refer to things that we just talked about. But it kind of worked out, right? I mean, that's kind of cool. All right, the q is the exclusive OR between the x and the y. So we have 0, 0, 0, 1 over here. And k0 is assumed 0 because we are not carrying a multi-chunk addition here. So k0 is assumed 0. So now when we look at this, there's a 1 here because 1 plus 1 has a carry of 1. And then when we look here, we also have 1 plus 1, which has a 1 over here. And then this one's going to be a 0 because 0 plus 0 has no carry of 1. 0 plus 1 does not have a carry of 1 either. So now we just have to find out what is the s bits. It's the exclusive OR between the q and the k, right? So q, k, exclusive OR 0, 0 has a 0, 0, 1 has a 1, 0, 1 has a 1, 1, 1 has a 1. So now we say the sum is 1110. How do we know 1110 is representing -2? Okay, so now the new question is 1110. Does it really represent -2? Because 3 minus 5 is -2, right? So we have to look at 1110 and ask, is it really representing -2? How do we know? How can we check using 2's complement? Negate and add 1, yes, but why does it work, right? So we want to find out, what is the negation of 1110, because we want that to be 2. So now we say, but negation is the same as 2's complement, or arithmetic negation is 2's complement. So now we take 2's complement of 1110, and we just expand it to be 1 plus the 1's complement, which is bitwise not of 1110, and that becomes 1 plus, we flip all the 1's into 0's, all the 0's into 1's, so we have 0, 0, 0, 1 in base 2 here, and that is 0, 0, 1, 0 in base 2, which is 2. Cool. Does that work for you guys? Does everybody see how, it just kind of works out? Okay. Very good. So 2's complement is how we perform arithmetic negation. So this can get us the representation of negative values if we choose to represent if we choose to use the signed representation when we have a fixed number of bits. All right. So if there are no questions, we'll go ahead and take a look at a few things. Okay, so these are terms that you need in order to do today's lab. Okay, so this is kind of important. We got about 15 minutes to do it, which I think is enough time, because it's really just a bunch of definitions. Okay, it's just a bunch of definitions. So we will mostly work with subtraction this time. Okay, so we'll go ahead and take a look at subtraction. So we can look at 0, 0, 1, 0 minus 0, 1, 0, 1. And so now we have x, y, q, and this is now called t because it's a subtraction, and this is called d because it is the difference. Okay, so this is nothing new. Okay, this part is not new at all. Okay, this is all binary subtraction stuff that we talked about last Thursday, and I'm hoping people have spent a little bit of time over the long weekend to review the material, because it's really crucial that we get the past material fully understood before we move on to the new material, which builds upon the older material. This Thursday, I believe we do have class on Thursday. Friday is a holiday, but not Thursday. Or am I incorrect? I typically don't keep track of holidays. What holidays are we talking about? All right. So Q is just exclusive OR. So we have 1, 1, 1, and then a 0 here. And then the borrow, is the only part that is a little bit tricky. So we got a 0 minus 1. We ends up with a borrow here. And then we don't have a borrow here. And then we have borrow here again. This is assumed to be 0. And then the D is the exclusive OR between the Q and the T. And we also have an extra borrow here, which is kind of important. So the Q and the T, when you exclusive OR those two, then we have so D would be a 1 here, 0 here, a 1 here, and a 1 here. So we don't know. Okay, so no one has looked up whether Thursday is a holiday for the school or not. I'm just going to look up on the side and find out los reals calendar. Okay. Academic calendar. That should have the holidays too, right? Yep, it does. Okay, it only says that the 12th is the Lincoln birthday, and then 15th is Washington birthday. Today is the 9th, so the 11th is not a holiday. So we do have class on Thursday. Oh, you guys can certainly make it a holiday and use up one of the unexcused absences. It's your choice. I mean, I'm not going to tell anyone whether to take it off or not, take a day off or not. I'm just repeating items in the syllabus. It is your choice. All right. So getting back to the tablet. Back to the tablet. All right. So now we got a few things. This column is called the most significant bit. Okay, and it is intentionally a lowercase b to signify that we are not talking about bytes, but bits. Okay, so this entire column are the most significant bits, except for t. Okay, this is the leftover t. This is also called the borrow. Okay, this is the borrow flag after an entire subtraction. The most significant bit is also called the sign bit. It is also called the sign bit because if we choose to interpret a 4-bit pattern like this in a signed way, that bit tells us whether the value being represented is negative or not. If the most significant bit is a 1, the value being represented is negative. If the sign bit is a 0, then the value being represented is non-negative. Is that okay? All right. So these are kind of important terms, okay? So now we have one extra term that is also important because you will need it in today's lab. It's called the overflow bit. So the B bit, in the lab today is really just referring to the overall borrow after a binary subtraction. That's the B for borrow flag. The overflow flag is a little bit interesting. So in this case, the overflow flag is x3 not y3 not d3, or not x3 y3 d3. Now remember, this or, this is really an or. Okay, it's not an actual addition. It is a or. Yes, B for borrow. Yep, that is correct. So B does not mean negative. Okay, B just means we need to borrow. We will talk about how to interpret these bits, later. The most significant bit of D, in other words, D3 in this case, is also referred to sometimes as the sign of the entire subtraction. That's I think that is useful, later on. So today, I think in the lab today, it is not important to know D3 also has a name of sign, the sign bit of the result of a subtraction. But the overflow flag is kind of important. Okay, I'm just looking at the time here. We got 10 minutes. Okay, so we can actually explain why the overflow bit is important. Okay, so we'll go ahead and illustrate it using a few examples. So we'll go ahead and ask, what is 1111 minus, oops, I take it back, sorry about that, 1000 minus 0001 in base 2. So once again, we got x, y, q, t, and then d all the way down here. So we'll go ahead and carry out this binary subtraction. 0 minus 1 is a 1 with a borrow of 1. 1 minus a 0 is a 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow of 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow of 1. 1 minus 0 is a 1. 1 minus 1 is a 0. So there's no overall borrow in this case. So in this particular case, the borrow flag is going to be a 0. The overall borrow of the subtraction is going to be a 0 because that 0 is that 0 over here. What about the overflow? So let's check out the overflow. So the overflow is 1, not 0, not 0, or 0, not 0. Let me erase that. Or not 1, 0, and 0. Okay, this one goes to here and also here. This 0, oh, this is going to look ugly, but I will try to make it less ugly. It goes here and it goes here, and then this 0 goes here and it goes here. All right. So in this case, we have 1 and 1 and 1 because not 0 is a 1, not 0 is a 1. This is all ANDed together. These are all ANDed together. So we end up with a 1 or 0. So overflow in this case is a 1. What does that mean? Right? We have to calculate it. It's not shown in the subtraction he's doing, right? The equation to do it is already shown here. We are just applying this equation to the specific bits that we have here. Alright, that question reflects a few things. I'm not gonna say much, but I would say, look up the binary subtraction module that we talked about last Thursday. As I said, it is important to review the material, especially after I have talked about it in class. Yes, Andrew is correct. Alright, so getting back to what you need to know for today's lab. Okay, what does it mean when we have an overflow? So now we want to look at x and y using signed and the unsigned interpretation. So I'll put it here: 1, 0, 0, 0 in base 2. We'll first start with the unsigned interpretation. So unsigned 1, 0, 0, 0 is representing 8. 0, 0, 0, 1 is representing 1. 0, 1, 1, 1 is representing 7. And you say, okay, well, that makes perfect sense. When you take 1 away from 8, it is 7, and we don't have an overall borrow. It makes sense, right? But when we look at this from the signed perspective, things are now a little bit tricky, because 1, 0, 0, 0 as in the signed representation is representing -8. 0, 0, 0, 1 is always just representing 1, and then 0, 1, 1, 1 in base 2 is representing 7. And you look at this and go like, but it doesn't make sense, Tech, because when you subtract a non-negative value from a negative value, you should always end up with a negative value. But not in this case. We end up with 7. Okay, positive 7. When you subtract 1 from -8, we end up with positive 7. The sign doesn't make sense. Okay, that is why the overflow is a 1. The overflow being a 1 means we ran out of values in signed representation, and as a result, the sign of the difference is wrong. Alright, I'm just checking the text channel, and looks like we got some side stream conversation going, but for the most part I'm not seeing any questions. So the overflow flag is significant because when we look at values from the signed perspective, when the result doesn't make any sense, the overflow bit or the overflow flag becomes a 1 to let us know and say, hey, something is not right here because I think we ran out of values that we can represent given the number of bits that we have. So overflow is only useful when we want to use the signed interpretation. When we want to look at things from the unsigned perspective, then overflow doesn't really, it doesn't really matter. We can still compute it, but it doesn't have any significance. So these are the two things that you need to know. Okay, one is the borrow flag, which is just the overall borrow after a subtraction. The other one is the overflow. So I believe now is a good time to open up the lab so that you guys can start to do it. So let me find the right tab. Okay, there we go. So this
Okay. Sorry, I don't mean to interrupt, but real quick, that's not a 0, it's a letter O for overflow, right?
that is a O. Yes, that is overflow.
Okay, just making sure. Thank you.
Okay. Yeah, so going back to here, I can do an OV for overflow, and OV over here. So overflow is OV, and 0 is just 0. I do apologize for the confusion because an O, uppercase O, and a 0 definitely look about the same. I should probably use a stroke across the 0 because that's how most people differentiate between the two. Alright, so the question is, so the overflow flag becomes a 1, not get triggered, when the result is a number outside of the range of signed representation. Yes, so you kind of have to be specific about what range we are talking about. We are talking about the range of signed representation, and then triggered is kind of being a 1. Okay. All right, so now we can open up this lab. It basically has 4 questions, if I remember correctly, and the 4 questions are in 2 batches. So you will see repeated type of questions. Some people are lucky enough to get exactly the same question, but that is very, very unusual. Okay. So we'll go ahead and release the lab, and I'll let you guys do it in the next 3 hours or so. Alright, so today is the 9th, and it is due at 9:50 p.m. I'm now very careful about when I mention the time, and maybe at some point I won't even say out loud. Okay, so you have about 3 hours to work on this. And then we have the key is flags. Okay, flags is the passcode, and once I save and publish, you guys should be able to get into it. Oh, you guys can hear whatever you want to hear. That is okay with me because everything is streamed to YouTube, and yeah, it's just like wait, I want Thursday to be a holiday. I don't want to be here. Well, okay, use up one of the unexcused absences. I'm not here to make your choices. I'm only here to enforce the consequences. Three hours would be 10:50. I think someone needs to go back and take remedial math classes. Oh yeah, I think a few people needs to go back and take remedial math classes. I can do a referral if you want to. Now Eric is the smart one. He said, well, we're using base 9. 6 plus 3 equals to 10. 1 0 in that case is not 10. Yep, we're using base 9 if that is the case. Yep. Alright, so we got the lab already released, and I'm just gonna do a quick preview over here just to make sure that everything in the lab is already mentioned in today's lab. So the sign bit is also known as the MSB. In the 4-bit subtraction, it is bit 3. Okay, let's consider the following subtraction. So these are all binary numbers. What is the overall borrow in the subtraction? Okay, we talked about that is the B flag when we talked about this. In the 4-bit subtraction, the overall borrow is the borrow from bit 4, not bit 3. Alright, so that is good. We talked about enough stuff to be able to answer that question. Okay, this is the one where we have the overflow flag. So this is an O, okay? It is not a 0, it is a uppercase O. And this time I use MS, SS, and DS to mean the most significant bits of the minuend, subtrahend, and difference. Minuend is what we otherwise know as X, subtrahend is what we otherwise know as Y, and D is the difference. So it is really the same thing, because the subscript S is kind of, referring to the most significant bit, and it is explained a little bit over here. MS is the sign bit of the minuend, SS is the sign bit of the subtrahend, DS is the sign bit of the difference. And if you didn't quite catch what when I explained what is the minuend, subtrahend, and difference, there's a link here. You can click on this link and find out what minuend, subtrahend, and difference refer to in a subtraction. That's the kind of sort of thing that I think people can look up. Question number 3. The sign bit is also known as the MSB. In the 4-bit subtraction, it is bit 3. Consider the following subtractions. So when we look at these subtractions, they're all in base 2. This is a super easy one, right? What is the sign bit of the difference, which is the most significant bit of the difference? Okay, so I think we know the answer to that one. And then we have the last one here, because I think we just have like 3 batches of the same kind of 4 questions. So question number 5 and question number 9 are very similar to question number 1, and so on. The sign bit is also known as the MSB. In the 4-bit subtraction, it is bit 3. Consider the following subtraction: 0, 1, 1, 1 minus 0, 1, 1, 1. That's an easy one. What is the overall borrow of the subtraction? In the 4-bit subtraction, the overall borrow is the borrow from bit 4, and it's basically T4. Okay, that's what it's saying. It's T4 and not T3. All right. What is question number 2 asking? Okay, let me go back and check that. Alright, so question number 2 is asking what is the overflow flag. So it's asking you to figure out the sign flag of the difference, then figure out the overflow value, the overflow bit value. This is the question. I want you guys to figure out the overflow. There we go. Yep, so Chris is correct. It is asking about the overflow flag, which is either 0 or 1. Alright, so I think that should be enough. I was just double checking to make sure that I have covered all of the concepts that we need to do this lab. And you guys can get started now, and I'll be on standby. Well, I'll be AFK for 10 minutes or so, and then I'll come back and start to answer questions. So if you have questions, go ahead and use direct message, because all of those will queued up in Discord, so I can actually tell who had the first question and so on. So that's what we'll do. I think I can stop the live stream now, so I'm gonna stop the voice streaming on Discord.